Throughout history, our planet has been shaped by powerful and often catastrophic natural events. From massive volcanic eruptions and devastating earthquakes to raging wildfires and cosmic explosions, these forces have repeatedly demonstrated their ability to alter landscapes, disrupt human civilization, and even change global climates. While scientific advancements have helped us understand these phenomena, they remain unpredictable, posing both immediate and long-term threats to life on Earth. The study of natural disasters not only sheds light on the mechanisms driving these events, but also helps us develop strategies to mitigate their effects. By examining historical incidents, current scientific research, and potential future scenarios, we can better prepare for the challenges that lie ahead. The impacts of these disasters extend beyond their immediate destruction. Volcanic eruptions can inject particles into the stratosphere, influencing global temperatures. Powerful earthquakes can reshape coastlines and trigger tsunamis. And solar storms have the potential to cripple modern technological infrastructure. In this document, we explore some of the most significant and impactful natural disasters of recent times. We begin with the eruption of the Hunga Tonga Hunga Ha'apai underwater volcano, one of the most powerful explosions ever recorded, and its widespread consequences. We then examine the devastating 2024 earthquake in Japan's Noto Peninsula, an unexpected event that caught scientists by surprise. The Australian wildfires, driven by record-breaking heat waves, demonstrate the increasing intensity of climate-related disasters. Looking beyond Earth, we analyze the potential threat of supernovae and how these cosmic explosions could impact our planet. The discussion continues with solar storms, particularly the historic Carrington event, and the risks posed by geomagnetic disturbances to our modern technological society. Finally, we address the pressing issue of climate change and resource depletion, emphasizing how human activity is influencing the planet's natural balance. By understanding these disasters, we not only gain insight into the forces shaping our world, but also learn how to protect ourselves from their most devastating consequences. The knowledge we gather today will be crucial in safeguarding future generations against the unpredictable and powerful forces of nature. The Hunga Tonga Hunga Ha'apai eruption in January 2022 was an extraordinary geological event, producing one of the most powerful volcanic explosions ever recorded. This underwater volcano, located in the South Pacific, had been exhibiting increased activity since late December 2021, leading up to a series of eruptions that culminated in a catastrophic explosion on January 14, 2022. What followed was a planetary-scale event that sent shockwaves across the globe, generated a tsunami, and significantly impacted the atmosphere. Scientists quickly realized that this eruption was unlike anything seen in modern history. The eruption of Hunga Tonga Hunga Ha'apai was so intense that it produced a pressure wave that traveled around the world multiple times. Satellite images captured the explosion as it unfolded, showing an enormous ash cloud that quickly expanded outward. Scientists compared the blast's force to the largest nuclear explosions ever detonated, estimating that it released energy equivalent to hundreds of atomic bombs. The eruption sent a massive column of ash, gas, and steam approximately 20 kilometers, 12.4 miles, into the atmosphere, reaching the stratosphere and affecting global weather patterns. Some estimates suggest that the eruption may have displaced as much as 10 cubic kilometers of material, making it one of the largest eruptions of the 21st century. Unlike typical land-based eruptions, the Hunga Tonga Hunga Ha'apai event was unique because it occurred underwater. When magma interacts with seawater, it can create explosive reactions due to the rapid expansion of steam. This phenomenon, known as phreatomagmatic eruption, was one of the primary reasons the explosion was so powerful. This underwater interaction also contributed to the vast amounts of water vapor injected into the atmosphere. Unlike ash and sulfur dioxide, which tend to have cooling effects by reflecting sunlight, water vapor is a greenhouse gas that can trap heat. Some researchers believe that the excess water vapor from this eruption may have had a short-term warming effect on the planet. The eruption's ash cloud spread across the Pacific region, covering nearby islands and affecting air quality. Ashfall was reported as far as Fiji and Australia, thousands of kilometers away. The fine volcanic ash, composed of tiny glass-like particles, posed serious health risks to residents and disrupted air travel. More significantly, the eruption had a measurable impact on global atmospheric circulation. Ash particles and gases reached the stratosphere, where they lingered for months, influencing cloud formation and weather patterns. Some scientists speculated that the eruption could lead to temporary disruptions in climate conditions, though the exact long-term effects remain under study. One of the most fascinating aspects of the eruption was the extraordinary display of volcanic lightning. Over 200,000 lightning flashes were recorded within the ash plume, making it one of the most electrically active volcanic events ever observed. Volcanic lightning occurs when charged particles in the ash cloud create an electrical imbalance, leading to powerful discharges. The eruption generated a powerful atmospheric shockwave that circled the Earth at least 4 times. This pressure wave was so intense that it was detected by weather stations worldwide, even in locations thousands of kilometers away. Additionally, the eruption triggered a tsunami that impacted coastal regions across the Pacific Ocean. While not as large as some historical tsunamis, the waves caused damage in places as far as Japan and Peru. Coastal areas in Tonga were hit hardest, with entire villages swept away by the waves. The tsunami underscored the potential for underwater volcanic eruptions to produce oceanic disturbances capable of traveling vast distances. Before the eruption, Hunga Tonga Hunga Ha'apai was a relatively young volcanic island formed by previous eruptions. However, the force of the January 2022 event was so immense that it obliterated much of the island, reducing it to 2 separate landmasses once again. Satellite images revealed that the central part of the island had collapsed back into the ocean, leaving a massive underwater crater where land had once been. The eruption of Hunga Tonga Hunga Ha'apai has provided scientists with a wealth of data to analyze. Because it was observed in real time using satellite technology, researchers have been able to study its effects in unprecedented detail. The event has raised important questions about how underwater volcanoes influence the atmosphere, ocean circulation, and global climate. One of the most significant discoveries has been the role of volcanic eruptions in injecting water vapor into the stratosphere. Unlike other major eruptions, which typically release large amounts of sulfur dioxide that lead to temporary cooling, this eruption's impact on climate remains a subject of debate due to its high water vapor content. Furthermore, the eruption has highlighted the need for improved early warning systems for underwater volcanic activity. While seismic monitoring and satellite imaging provide valuable insights, predicting such powerful eruptions remains a significant challenge. The Hunga Tonga Hunga Ha'apai eruption was a stark reminder of the power of natural forces and their ability to reshape the planet. From atmospheric shock waves and volcanic lightning to tsunamis and widespread ash fallout, the eruption showcased the interconnectedness of Earth's systems. While much remains to be studied, this event has provided a crucial case study in understanding how underwater volcanic eruptions impact both local and global environments. The lessons learned from this eruption will undoubtedly play a role in improving our ability to monitor and predict future geological disasters. The Noto Peninsula Earthquake, January 2024. On January 1st, 2024, the Noto Peninsula in Japan experienced a devastating magnitude 7.5 earthquake, causing widespread destruction and a humanitarian crisis. This powerful quake struck a region not typically associated with large seismic events, making it a shocking occurrence for both residents and scientists alike. The earthquake was followed by over 1,200 aftershocks, some of significant magnitude, prolonging the devastation and complicating rescue and recovery efforts. Japan is one of the most seismically active countries in the world, sitting at the convergence of multiple tectonic plates. However, the Noto Peninsula is not located on any major fault line, which made this event particularly surprising. In contrast to the usual subduction zone earthquakes that Japan frequently experiences, this earthquake occurred within the continental crust, leading to a different pattern of destruction. Prior to the main event, the region had been experiencing an earthquake swarm since 2020. Thousands of small tremors recorded over 4 years. While scientists observed and documented this phenomenon, there was no clear indication that it would culminate in such a catastrophic quake. The unpredictability of this event raises critical questions about seismic forecasting and the limitations of current earthquake prediction models. The earthquake claimed the lives of at least 241 people and left nearly 1,300 others injured. Thousands of buildings, roads, and critical infrastructure were severely damaged or completely destroyed. The financial toll of the disaster is estimated at over $18 billion, a significant blow to Japan's economy. Beyond the economic and infrastructural damage, the earthquake caused massive displacement, with tens of thousands of people forced to evacuate. Relief efforts were hindered by aftershocks, landslides, and damaged roads, making it difficult for aid workers to reach the hardest-hit areas. One of the most striking consequences of the earthquake was the sudden change in land elevation across the Noto Peninsula. Some areas experienced an uplift of up to 4 meters, 13 feet, permanently altering the coastline. This type of tectonic movement has long-term implications for both natural ecosystems and human infrastructure. Rising land levels can alter water drainage patterns, impact marine habitats, and require extensive rebuilding of coastal facilities. Major earthquakes can slightly alter the distribution of Earth's mass, leading to subtle changes in the planet's rotation. Scientists have measured minor variations in the length of a day following large seismic events, similar to what was observed after the 2011 Tohoku earthquake. While these changes are minute, on the order of microseconds, they demonstrate how interconnected the Earth's systems are. Even a localized event can have ripple effects on a planetary scale. One of the biggest mysteries surrounding the Noto Peninsula earthquake is the prolonged period of seismic activity leading up to it. Since 2020, scientists have recorded tens of thousands of small quakes in the region. an unusual phenomenon for an area without a known major fault line. Typically, earthquake swarms occur near volcanic regions or along subduction zones. Yet the Noto Peninsula does not fit either of these criteria. Theories for the cause of this prolonged seismic activity include deep fluid movement. Some geophysicists suspect that underground fluids, possibly water or magma, may have been moving through fractures in the crust, gradually increasing stress until it resulted in a larger quake. Slow tectonic stress accumulation. While the region lacks a major fault line, long-term tectonic stress could have been building up over centuries, finally reaching a breaking point in 2024. Hidden fault systems. It is possible that previously unidentified faults exist beneath the region, and this earthquake may have been the result of a rupture in one of these hidden structures. Further research and aftershock analysis will be necessary to determine the exact cause of this unexpected disaster. The Noto Peninsula earthquake underscores the need for improved earthquake prediction and early warning systems. Japan's current warning system is among the most advanced in the world, but this event highlights its limitations. Seismologists are now focusing on enhanced seismic monitoring, installing more sensors in less studied regions to detect early warning signs, AI and machine learning applications, using big data analysis to identify patterns in earthquake swarms that could indicate a larger quake is imminent. Improved public awareness and preparedness. Given the unexpected nature of this earthquake, raising awareness and preparing for seismic events, even in regions not considered high risk, is crucial. The 2024 Noto Peninsula earthquake serves as a stark reminder of the unpredictability of natural disasters. Despite advancements in seismic research, earthquakes remain difficult to forecast with precision. The destruction caused by this event has left lasting impacts on both the affected communities and the scientific community's understanding of seismic activity in Japan. As rebuilding efforts continue, the disaster also reinforces the importance of resilient infrastructure, comprehensive disaster preparedness plans, and continued investment in earthquake monitoring technology. The lessons learned from this earthquake will not only aid in Japan's future preparedness, but also contribute to global efforts to mitigate the impact of similar seismic events worldwide. Wildfires in Australia. Australia has long been known for its harsh climate, but the summer of 2019 to 2020 brought an unprecedented catastrophe. A prolonged drought, combined with record-breaking temperatures exceeding 41 degrees Celsius, 105.8 degrees Fahrenheit, created the perfect conditions for one of the most devastating wildfire seasons in recorded history. This period, later termed the Black Summer, saw fires ravage vast portions of the Australian landscape, destroying ecosystems, claiming lives, and emitting massive amounts of carbon dioxide into the atmosphere. The wildfires in Australia were fueled by an ongoing multi-year drought that had left much of the country's vegetation dry and highly flammable. The Australian climate is largely influenced by El Niño Southern Oscillation (ENSO) cycles, which affect rainfall patterns and temperature fluctuations. During the Black Summer, the nation experienced one of its driest years on record, exacerbating fire risks. Additionally, Australia's naturally flammable eucalyptus forests acted as a catalyst for the fires. Eucalyptus trees contain volatile oils that make them highly combustible, contributing to the rapid spread of wildfires. Combined with strong winds and erratic weather patterns, the fires quickly escalated beyond control. The Black Summer fires burned over 10.7 million hectares, 26.4 million acres of land, an area larger than the entire country of South Korea. This destruction surpassed the combined total area burned in the Amazon and California wildfires of the same period. The fires destroyed more than 3,500 homes and damaged thousands of additional structures. Several small towns were almost completely obliterated. In New South Wales alone, over 80% of the Blue Mountains World Heritage Area was affected by the fires, a staggering loss for both biodiversity and cultural heritage. The wildfires led to at least 33 human fatalities, including firefighters and civilians. Thousands more suffered from severe burns and smoke inhalation-related illnesses. However, the most shocking loss was to Australia's wildlife. Scientists estimate that over 3 billion animals were impacted by the fires, including kangaroos, koalas, and countless bird species. Many species that were already endangered faced severe habitat destruction, pushing them closer to extinction. One of the most dangerous aspects of the Australian wildfires was the formation of pyrocumulonimbus clouds, massive fire-generated storm clouds that can reach the stratosphere. These clouds act like volcanic eruptions, injecting smoke and particulate matter high into the atmosphere. They also generate lightning, which can ignite new fires, creating a self-sustaining feedback loop of destruction. Scientists observed that at least 30 pyrocumulonimbus events occurred during the Black Summer, a record-breaking number. These clouds transported smoke across the Pacific Ocean, reaching South America and even influencing weather patterns in Antarctica. Smoke from the wildfires blanketed major Australian cities, turning skies an eerie orange and causing hazardous air quality levels. In Sydney, air pollution reached over 11 times the hazardous threshold, causing respiratory illnesses to spike. People were advised to stay indoors, and schools were temporarily closed in some regions due to unsafe conditions. The health impacts of the prolonged smoke exposure included increased hospital admissions for asthma and other respiratory diseases, higher rates of heart attacks and strokes, long-term concerns over lung damage and cancer risks. One of the most alarming aspects of the Australian wildfires was their impact on global carbon emissions. The fires released an estimated 830 million metric tons of CO2 into the atmosphere, more than the annual emissions of Germany. This massive release of greenhouse gases contributed to the climate feedback loop, a process where warming temperatures create conditions that lead to more wildfires, which in turn release more CO2, further exacerbating global warming. This cycle makes future fires more frequent and intense, posing a significant challenge for climate change mitigation. Following the Black Summer, Australian authorities have re-evaluated their approach to fire prevention and management. Some key strategies include controlled burns, increasing the use of prescribed burning to reduce fuel loads in forests before the peak fire season. Early warning systems, implementing better fire detection technologies, including satellite monitoring and AI-driven fire forecasting. Community preparedness, educating residents on evacuation protocols and fire-resistant home designs. Given that climate change is increasing the frequency of extreme weather events, governments and scientists are pushing for stronger climate adaptation policies. This includes strengthening building codes to make homes more fire-resistant, expanding reforestation efforts to recover lost habitats, enhancing international cooperation to address the global wildfire crisis. The wildfires in Australia were a stark reminder of the destructive power of nature, amplified by human-driven climate change. As wildfires become more intense and widespread, governments, scientists, and communities must work together to develop effective mitigation and adaptation strategies. The Black Summer was a turning point in how the world views wildfires. No longer confined to specific regions, fire disasters are now a global issue, requiring urgent action to prevent even greater devastation in the future. Supernova: threats to Earth. Among the most violent and awe-inspiring phenomena in the universe, a supernova is the explosive death of a massive star. For a brief moment, a supernova can outshine an entire galaxy, releasing immense amounts of energy and scattering heavy elements across the cosmos. While these events play a crucial role in shaping the universe, they also pose potential risks to Earth, particularly if one were to occur relatively close to our planet. A supernova occurs when a star reaches the end of its life cycle and undergoes a sudden, catastrophic explosion. There are two main types of supernova. Type 1, supernova. These occur in binary star systems where a white dwarf accumulates matter from its companion star until it reaches a critical mass, triggering a thermonuclear explosion. Type 2, supernovae. These happen when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel, causing its core to collapse under gravity, leading to a colossal explosion. In both cases, the explosion releases vast amounts of radiation, including gamma rays, X-rays, and cosmic rays, which can have far-reaching consequences on surrounding planets, including Earth. If a supernova were to occur within 25 light-years of Earth, the high-energy radiation emitted could strip away the planet's ozone layer. The ozone layer protects life on Earth from harmful ultraviolet, UV, radiation from the Sun. Without it, increased UV exposure would lead to higher rates of skin cancer and cataracts in humans and animals, severe damage to phytoplankton, disrupting the marine food chain, negative effects on plant life, reducing agricultural yields. A supernova-induced ozone depletion could take years or even decades to recover, causing widespread disruptions to ecosystems and human civilization. While no recorded supernova has directly impacted modern human civilization, scientists speculate that past supernova may have contributed to mass extinctions. Some key findings include 2.5 million years ago. Geological evidence suggests that a supernova explosion may have showered Earth with iron-60 isotopes, possibly triggering climate changes and affecting early hominid species. 13,000 years ago, some researchers propose that a supernova explosion could have contributed to the extinction of woolly mammoths by increasing atmospheric radiation and disrupting ecosystems. Medieval records. Ancient astronomers documented bright guest stars appearing in the sky, which we now identify as supernovae, such as SN 1006 and SN 1054, the latter of which created the Crab Nebula. One of the closest and most well-known supernova candidates is Betelgeuse, a red supergiant in the constellation Orion. At approximately 642 light-years away, Betelgeuse is nearing the end of its life and could explode any time in the next few thousand years. When it does, it will be one of the brightest objects in the night sky, visible even during the day. Fortunately, because of its distance, Betelgeuse's supernova will not pose a direct threat to Earth. However, it will provide scientists with a unique opportunity to study a nearby stellar explosion in real time. Are there any dangerous supernova candidates near Earth? Astronomers have identified several potential supernova candidates, but none are close enough to cause catastrophic damage to Earth. The nearest massive stars expected to go supernova in the distant future are Antares, 550 light-years away, Spica, 250 light-years away, Rigel, 860 light-years away. All of these stars are far enough that their eventual explosions will not have significant negative effects on Earth. What would happen if a nearby supernova occurred? If a supernova were to occur closer than 50 light-years, Earth could experience a massive surge in cosmic radiation, potentially increasing cancer rates and mutating DNA. Damage to satellites and electronic systems as high-energy particles disrupt electronics. A visible celestial event, where the explosion would appear as bright as the full moon for weeks or months. If a supernova were to occur within 10 light-years, it could lead to a major extinction event, wiping out large portions of life on Earth due to radiation exposure and environmental disruptions. While the idea of a nearby supernova is alarming, current astronomical observations suggest that Earth is relatively safe from such an event. No known supernova candidates are close enough to pose a significant risk in the near future. However, continued research into stellar evolution and cosmic radiation remains crucial to understanding and preparing for any potential threats from space. Supernovae serve as both a reminder of the dynamic nature of the universe and a source of scientific discovery. They are responsible for creating many of the elements that make up planets, life, and even our own bodies. Understanding their role in the cosmos not only helps us assess their risks, but also deepens our appreciation for the vast and ever-changing universe in which we live. Solar storms and the worst-case scenario. In September 1859, a massive solar storm, now known as the Carrington event, struck Earth with an intensity never before recorded. This geomagnetic storm was so powerful that it disrupted telegraph systems worldwide, causing widespread failures and even giving telegraph operators electric shocks. The auroras produced by the storm were so bright that people in the Caribbean, Mexico, and even sub-Saharan Africa reported seeing the sky illuminated as if it were daytime. The event was named after British astronomer Richard Carrington, who observed the massive solar flare responsible for the storm. The coronal mass ejection, CME, from the Sun traveled to Earth in just 17.6 hours, an incredibly fast speed, indicating an unusually powerful solar burst. The storm's impact was relatively limited due to the technology of the time, but if a similar event were to occur today, the consequences would be far more severe. Modern-day implications. What would happen if a similar solar storm struck today? A Carrington-level event occurring today could trigger a global technological disaster. Our modern world relies heavily on electronic systems, satellite communications, and interconnected power grids, all of which are extremely vulnerable to the electromagnetic disturbances caused by a powerful geomagnetic storm. Scientists predict that a major solar storm today could cause trillions of dollars in damages, potentially collapsing power grids worldwide and sending modern civilization into chaos. The electrical grid is one of the most vulnerable systems to solar storms. In the event of a massive geomagnetic storm, power transformers and transmission lines would experience intense electrical surges, leading to widespread blackouts lasting weeks or even months. Permanent damage to transformers requiring years of replacements. Massive economic losses, with estimates reaching up to $2.6 trillion in the US alone. Modern society depends heavily on satellites for navigation, communication, and weather forecasting. A strong solar storm could knock out GPS satellites, disrupting transportation, aviation, and military operations. Damage communication satellites, affecting mobile networks, internet connectivity, and TV broadcasts. Interfere with space missions, causing potential risks to astronauts aboard the International Space Station, ISS. A global-scale internet blackout could result from damage to undersea fiber optic cables, which rely on repeaters powered by electrical systems vulnerable to geomagnetic disturbances. Experts warn that financial markets could collapse due to disrupted communications between banks and stock exchanges. Emergency services and disaster response operations would struggle to function. Millions of businesses worldwide would face unprecedented disruptions, leading to economic recession. During a major solar storm, the increased radiation could be hazardous for airline passengers and crew, particularly on long-haul flights crossing polar regions. Potential risks include increased cancer risks from exposure to high-energy particles, electronic failures in aircraft navigation systems, potential grounding of flights for safety reasons. In response to the threat of massive solar storms, the U.S. has implemented the Solar Shield program, designed to monitor solar activity and provide early warnings. This program involves real-time monitoring of the sun's activity using NASA and NOAA satellites, predictive modeling to estimate the intensity and arrival time of CMEs, protective measures for power grids, such as shutting down transformers before a major storm hits. However, despite this initiative, most countries remain unprepared for a large-scale solar storm. The lack of international coordination in solar storm preparedness could lead to catastrophic global consequences. How likely is another Carrington-level event? Scientists estimate that a solar storm of Carrington event magnitude has about a 12% chance of occurring within the next decade. While this may seem like a low probability, the potential devastation means that governments and industries must take this threat seriously. The most recent near miss occurred in July 2012, when a superstorm-sized CME was ejected from the sun. Fortunately, it missed Earth, but had it struck, it could have caused significant disruptions to global infrastructure. The event served as a stark reminder that another Carrington event is not a question of if, but when. A major solar storm is one of the most underestimated threats to modern civilization. With our increasing reliance on technology, the potential damage from a powerful geomagnetic storm has never been higher. The Carrington event of 1859 serves as both a warning from history and a reminder of the sun's immense power. To mitigate the risks, governments must prioritize solar storm preparedness. Power companies must implement grid protection measures, and the world must work together to develop global early warning systems. As we continue to study space weather and its potential effects, proactive action is crucial to ensuring that human civilization remains resilient in the face of cosmic forces. Climate change and resource depletion. For over 500,000 years, atmospheric carbon dioxide, CO2, levels have fluctuated within a natural range. Yet human activity has drastically altered this balance. Today, CO2 concentrations exceed 400 parts per million, a threshold not seen in 500,000 years. This unprecedented rise is directly linked to fossil fuel combustion, deforestation, and industrial emissions. CO2 acts as a greenhouse gas, trapping heat in the Earth's atmosphere. As a result, global temperatures have risen at an accelerated rate, causing significant environmental consequences. Melting ice caps, the Arctic and Antarctic ice sheets, are losing mass at alarming rates, contributing to rising sea levels and threatening coastal communities. More frequent extreme weather, heat waves, hurricanes, and heavy rainfall events have intensified due to shifting climate patterns. Ocean acidification. CO2 dissolves into seawater, forming carbonic acid, which lowers pH levels and endangers marine ecosystems. Fossil fuels have been the foundation of industrial civilization, providing energy for transportation, manufacturing, and electricity generation. However, these resources are finite, and their depletion raises concerns about future energy security. Current estimates suggest that oil and natural gas reserves could be exhausted within the next 50 to 100 years. The increasing difficulty of extracting these resources has led to higher production costs, greater reliance on environmentally damaging extraction methods, e.g. hydraulic fracturing, deep-sea drilling, geopolitical tensions over remaining reserves. Coal remains more abundant than oil or natural gas, with reserves potentially lasting another 100 to 150 years. However, coal is also the most carbon-intensive fossil fuel, responsible for 40% of global CO2 emissions. While technological advancements like carbon capture and storage, CCS, offer potential solutions, widespread adoption remains slow due to high costs and political resistance. Should modern civilization collapse due to environmental disasters, war, or economic turmoil, rebuilding to current technological levels would be significantly more difficult due to resource depletion. The Industrial Revolution was fueled by easily accessible coal, oil, and natural gas deposits. Future civilizations, however, would lack these easily reachable energy sources, making industrialization much harder. Deep extraction requires advanced technology, which would not be available in a post-collapse society. Without fossil fuels, producing steel, concrete, and plastics at an industrial scale would be nearly impossible. While renewable energy sources such as solar, wind, and hydroelectric power offer a sustainable path forward, their infrastructure requires fossil fuels for production, transportation, and installation. If civilization were to regress technologically, restarting large-scale renewable energy deployment would be difficult. Modern agriculture relies on fossil fuels for synthetic fertilizers derived from natural gas, mechanized farming equipment powered by diesel and gasoline, global food transportation networks dependent on oil. Without these inputs, feeding a large population would become a monumental challenge. The twin crises of climate change and resource depletion pose existential threats to human civilization. To ensure long-term survival, global efforts must focus on reducing CO2 emissions through clean energy transitions and reforestation initiatives, investing in renewable energy infrastructure before fossil fuel reserves become critically low, developing sustainable agriculture practices that rely less on fossil fuels. Failure to act decisively could leave future generations struggling to rebuild, trapped in a cycle of environmental and resource crises. The time to implement sustainable solutions is now, before our planet reaches an irreversible tipping point. These interconnected disasters highlight the fragility of human civilization in the face of natural forces. While scientific advancements help us predict and mitigate some risks, many challenges remain. Climate change, resource depletion, and natural disasters are not isolated events. They form a web of cascading effects that impact global stability. Understanding these phenomena allows us to better prepare for the future, ensuring resilience against unpredictable forces. Investing in sustainable energy sources, improving disaster preparedness, and developing innovative technologies will be key to adapting to these evolving threats. Governments, corporations, and individuals must work together to implement solutions that balance economic growth with environmental responsibility. The choices we make today will shape the world for future generations. Will we rise to the challenge and build a sustainable future? Or will we allow short-term interests to dictate the fate of our planet? The answer lies in our collective actions and commitment to progress. The resilience of humanity depends on our ability to adapt, innovate, and prioritize sustainability over convenience. Only through proactive efforts can we secure a thriving and habitable Earth for the centuries to come. Thank you for watching. If you enjoyed the content, don't forget to like and subscribe to support me.